Welcome to Keentel Engineering, data center design for grid reliability, designing for uptime, grid reliability, and scalable growth. This briefing is based on NERC's July 2025 white paper on emerging large loads. By 2028, data centers are forecast to represent 12% of all U.S. electricity consumption, up from 4.4% in 2023. One event in 2024 lost 1,500 megawatts of data center load simultaneously. Grid reliability and facility uptime are the same engineering problem. Let's get into it. The numbers are clear. Data centers are forecast to reach 12% of all U.S. electricity consumption by 2028. In 2023, that figure was 4.4%, a tripling in 5 years. NERC has formally classified large data center loads as grid consequential, not passive. The July 2025 white paper is the official reliability framework. The growth driver is AI compute, training and inference at hyperscale. Data centers are now the fastest growing energy consumer in North America. The grid was not designed for this pace of growth. NERC's July 2025 paper marks a formal shift in how data centers are classified. The old view, static predictable load, design stops at the building fence, generator plus UPS equals sufficient. One-size-fits-all templates, utility engagement is a late-stage task, and megawatt rating is the only metric that matters. The new reality: dynamic power electronic heavy systems, grid behavior engineered inside the fence, ride-through, ramp rates, and harmonics all matter. AI and traditional loads need different designs. Interconnection is a technical engineering task, and ramp rate, voltage sensitivity, and operating behavior all count. That shift from old to new is the entire premise of this presentation. Not all data centers are the same, and designing them with the same template is an engineering error. Traditional data centers, typically under 30 megawatts, stable predictable load, slow ramp rates in minutes, full UPS on all IT load, steady cooling at 10 to 20% of total load. Standard interconnection application. AI training facilities, 100 to 500 megawatts, and growing cyclic fast ramping load, ramp rates of 1.9 per unit per second for 250 milliseconds, checkpoint recovery with partial UPS, cooling up to 40% of total load with VFD heavy variability. EMT, SSCI, ramp, and harmonic studies required. Utility-ready technical package mandatory. The electrical design must follow the workload, not a generic template. NERC documented this. At time 0, 450 megawatts. Full AI training load at a hyperscale campus. Steady state demand at 36 seconds, 40 megawatts. The full campus drops to near idle. 410 megawatts vanishes from the grid without warning. 4 hours later, 7 megawatts. Checkpoint saving mode. Sustained for 4 hours while the grid absorbs a new generation surplus it wasn't expecting. Then, the campus returns to 450 megawatts within minutes. NERC's conclusion: rapid load shifts challenge reserve procurement, frequency regulation, and voltage control simultaneously. This is a single facility, one event, 450 megawatts. NERC frames data center electrical architecture as 4 systems, and all 4 must be designed as one integrated problem. 1. IT equipment. 60 to 95% of total load. CPUs, GPUs, AI accelerators, storage. The most dynamic component. AI training creates sub-second load pulses. Must be characterized by workload, not nameplate megawatts. 2. Power delivery. Service entrance to IT rack. Utility feed, transformers, switchgear, UPS, generators. The interconnection point defines grid behavior. Ride-through, protection coordination, and backup sequencing must be designed together. 3. Cooling. 10 to 40% of total load. VFDs and power electronics introduce harmonics. Cooling load is variable and reactive, must be included in harmonic and stability studies. 4. MISC infrastructure, BMS, fire suppression, lighting, access control, often overlooked. Relevant for staged restoration planning and energization sequencing ride-through is how a facility behaves during voltage and frequency disturbances, and how that behavior affects the wider grid. NERC documented approximately 1,500 megawatts lost in a single event from data center tripping. 5 design requirements for stable ride-through. 1. Voltage sensitivity characterization. Define at what voltage level the facility transfers to backup. Coordinate with UPS and protection settings, not vendor defaults. 2. Backup transfer logic. Transfer must be deliberate and sequenced. Uncoordinated transfer of large blocks causes sudden demand spikes visible system-wide. 3. Reconnection philosophy. Voltage ramped re-energization, not instantaneous reconnect. 4. Protection coordination study. UPS, generators, feeders, and utility relaying must all coordinate. Misoperation at any layer can cascade to a grid-level event. 5. Dynamic study support. Ride-through behavior must be verified in transient and EMT simulations, not assumed from equipment spec sheets. NERC is direct. Data centers are major sources of harmonics due to power electronics in both IT systems and cooling infrastructure. 4 risks. 1. Harmonic distortion. Switching converters in UPS and VFDs inject harmonics. Without deliberate filter design, distortion levels push utilities toward penalties or forced mitigation. 2. Voltage flicker. Rapid AI load transitions create voltage fluctuations visible on the wider system. UPS output can oscillate under some control modes. 3. Reactive power demand. Cooling VFDs and power electronics make the facility a significant reactive load, affecting voltage regulation at the point of interconnection. 4. Unbalance and instability. Asymmetric loading and resonance between UPS input filters and grid impedance create oscillation conditions that standard phasor models don't see. 9 service areas, 1 integrated engineering engagement, utility, and interconnection. Readiness, conceptual one-lines, demand block definitions, staged energization strategy. MV and LV electrical design, distribution, switchgear, transformers, busway, cable sizing. Backup and UPS architecture, generator plant design, topology selection, transfer logic. Load characterization, workload-informed ramp modeling, operating modes, transition sequences. Ride-through and protection. Voltage sensitivity, relay coordination, reconnection philosophy. Harmonics and reactive power. Filter strategy, reactive assessment, VFD interaction analysis. Telemetry and observability, PMU integration, high-resolution disturbance recording, model-ready data. Phased energization planning, load block sequencing, restoration order, black start compatible logic, and study support and compliance. NERC, PRC, MOD, TPL, and large load interconnection coordination. Design for what's inside, build for what's outside. The future belongs to firms that engineer both sides of the fence. For owners and developers, start before permits. Grid behavior is a design variable, not a commissioning surprise. Engage interconnection engineering at concept stage. For hyperscalers and EPCs, characterize the workload. AI training and cloud inference have different load signatures. Generic templates produce generic results. For utilities and planners, demand the data package, ramp behavior, protection settings, operating modes, and dynamic models required before study, not after energization. Keentel Engineering. Reach us at keentelengineering.com.